When we say that space and time are not separate things but part of one single fabric, we are challenging one of the most natural assumptions the human mind makes. From the moment we are children, we learn to divide the world neatly. There is where something is, and there is when something happens. A toy is on the floor, that is space. Dinner is at 7 o'clock, that is time. Our language, our habits, and even our emotions reinforce this division. Space feels solid and visible. Time feels invisible but steady, like a clock ticking in the background. For most of human history, this separation seemed obvious and unquestionable. Even the greatest thinkers assumed that space was a rigid stage and time was a universal ticking clock shared by everyone, everywhere. Richard Feynman would start by gently shaking this assumption, not by attacking it, but by showing why nature itself does not respect that separation. In physics, an event is the most basic unit of reality. An event is something that happens: a flash of light, a particle collision, a heartbeat, a star exploding. And every event must be described by both where it happens and when it happens. If you try to describe only one of those, your description is incomplete. Saying, "the explosion happened," means nothing unless you also say where. Saying, "it happened there," means nothing unless you also say when. From the universe's point of view, these two pieces of information are inseparable. They come as a package. This is where the idea of space-time begins. Instead of imagining space as a three-dimensional box and time as a separate line flowing forward, physics combines them into a four-dimensional structure. 3 dimensions of space and 1 dimension of time are woven together. This does not mean that time suddenly feels like space in everyday life. You cannot walk backward in time the way you walk backward in a room. But it does mean that, mathematically and physically, space and time are deeply linked. Changing how one behaves affects the other. Feynman loved to emphasize that physics is not about how things feel, but about how they behave. Feelings can mislead us. Space feels solid and time feels constant, but experiments tell a different story. When scientists began measuring the behavior of light and motion with great precision, they discovered something shocking. The speed of light is always the same, no matter how fast the observer is moving. This simple fact breaks the old idea of separate space and time. To keep the speed of light constant for everyone, nature must allow distances to change and time intervals to stretch or shrink depending on motion. This is not a philosophical trick. It is not a matter of perspective or illusion. It is how the universe actually works. If two people move differently through space, they also move differently through time. Their measurements of distance and duration will not agree, and yet both measurements will be correct within their own frame of motion. Space and time adjust together to preserve the deeper structure of space-time. To make this idea intuitive, Feynman would often use simple mental pictures. Imagine drawing a map. A map shows locations, distances, and directions. Now imagine that every point on the map also has a clock attached to it. Every event in the universe is a dot on this map with a time stamp. The universe does not care about space alone or time alone. It cares about these dots, these events in space, time. Physics is the study of how these dots are connected, how they influence one another, and how patterns emerge from their relationships. Before Einstein, scientists believed that space was absolute. It existed independently of what was inside it. Time was also absolute, flowing at the same rate everywhere, like a cosmic metronome. Feynman would point out that this idea worked well for everyday life, just as the idea that the Earth is flat works well for walking to the store. But when you look closely enough, or when you move fast enough, the approximation breaks down. Nature reveals its deeper rules. In this deeper view, space-time is not just a passive container. It is an active participant in the universe. Objects do not merely exist in space-time, they interact with it. Motion through space affects motion through time. Energy and mass influence the structure of space-time itself. This is not something we invented for mathematical beauty. It is something the universe demands. Feynman would likely pause here, and remind you that confusion is a sign you are learning something real. When ideas feel strange, it is often because they do not fit neatly into the boxes your mind was trained to use. Space and time being one fabric feels strange because our brains evolved to survive, not to understand relativity. But the universe is under no obligation to match our intuitions. To understand why space and time must be unified, consider communication. Suppose you send a message by flashing a light. That light travels at a fixed speed. If someone far away sees the flash, the timing of that event depends on their motion relative to you. If space and time were truly independent, there would be a single universal answer to when the flash happened. But there isn't. Different observers legitimately disagree. The only way to make sense of this without contradictions is to accept that space and time mix together. What one observer calls a difference in time, another observer may call a difference in space. This mixing is not arbitrary. It follows precise mathematical rules. Feynman would stress that this is one of the most beautiful aspects of physics. Nature is strange, but it is not sloppy. The equations that describe space-time are elegant and exact. They tell us how measurements transform from one observer to another, how cause and effect are preserved, and why no information can travel faster than light. Another way to think about the unity of space and time is to consider cause and effect. For something to cause something else, it must happen close enough in space and time for a signal to travel between them. Time defines what can influence what. It draws boundaries between events that can be connected and events that cannot. These boundaries are not drawn separately in space and time. They are drawn in space-time. This is why the structure of space-time is fundamental to understanding reality itself. Feynman would also emphasize that this idea is not just theoretical, it has practical consequences. GPS satellites, for example, must account for the fact that time flows differently for them than it does on Earth. Their clocks tick at slightly different rates because of their motion and their position in Earth's gravitational field. If engineers ignored the unity of space and time, GPS would quickly become useless. Your phone would not know where you are. The idea of space-time also prepares us for understanding gravity in a new way. Once you accept that space and time form a single fabric, it becomes natural to ask whether that fabric can bend or stretch, and it can. Mass and energy change the geometry of space-time. This is not a force in the traditional sense. It is a change in the shape of the stage itself. Objects move the way they do because they are following the geometry of space-time. But even without going that far, the first and most important step is recognizing that space and time are not independent ingredients mixed together later. They are born together. Every event carries both aspects inherently. You cannot peel time away from space or space away from time without breaking the description of reality. Feynman would likely end this part of the explanation by reminding you that the goal is not to memorize words like four-dimensional manifold or space-time continuum. The goal is to change how you think. Instead of asking, "Where is it?" and "When did it happen?" as two separate questions, physics teaches us to ask a single question. Where and when did it happen? That shift, small as it sounds, is one of the greatest changes in human understanding. Once you truly absorb this idea, many other mysteries become less intimidating. Time slowing down, lengths shrinking, gravity bending the universe, black holes, and even the origin of the cosmos all grow out of this single insight. Space and time are not separate actors performing on the same stage. They are threads of the same fabric, woven together so tightly that pulling on one always moves the other. To continue this way of thinking, it helps to let go of the idea that space-time is something exotic reserved only for extreme situations like black holes or spaceships moving near the speed of light. Feynman would insist that space-time is always there, quietly shaping every moment of your life, even when nothing dramatic seems to be happening. You are moving through space-time right now simply by sitting and reading. You are not only traveling through time second by second, You are also traveling through space as the Earth rotates, orbits the Sun, and moves through the galaxy. Your path through the universe is a continuous line drawn through space, time, whether you are aware of it or not. This path is often called a world line, though Feynman would avoid fancy terms unless they were absolutely necessary. He might say instead, imagine drawing a line that shows your entire life, not just where you went, but when you were there. Your birth is one point on that line. Every step you take adds another point. That line never leaves space-time because there is nowhere else to go. Everything that exists traces out such a line, from an electron to a galaxy. Once you accept that everything traces a path through space-time, motion takes on a new meaning. Motion is no longer just moving through space as time passes. Motion is a particular way of moving through space-time. Different motions correspond to different shapes of paths. Standing still on Earth is not actually standing still in space-time. It is a specific curved path caused by Earth's gravity and motion. Flying in an airplane, orbiting in a satellite, or drifting freely in space all correspond to different paths, even if they feel similar from the inside. Feynman would emphasize something subtle here. The laws of physics care about these paths, not about your personal feelings of motion or rest. There is no absolute state of rest in the universe. There is no cosmic reference point that says, this is truly standing still. All motion is relative, and space-time is the arena that makes this relativity precise. What matters is how one path compares to another. This leads naturally to the idea that time itself depends on the path you take. If two people start together and later meet again, they may have experienced different amounts of time depending on how they moved through space-time. This is not a trick or a paradox. It is a direct consequence of space and time being one fabric. Different paths through that fabric have different lengths, and that length corresponds to how much time passes for the traveler. Feynman would likely pause here to reassure you that this does not destroy cause and effect. Even though observers disagree about distances and durations, they never disagree about what can cause what. Space-time has a built-in structure that preserves causality. Events that can influence each other lie within certain regions of space-time. Events outside those regions are forever disconnected. This structure is not imposed by us. It is discovered by experiment and encoded in the geometry of space-time itself. To a child, he might explain it like this: imagine you can shout, but your voice only travels so fast. If someone is too far away, they cannot hear you shout right now, no matter how loud you are. Space-time works the same way, except the shout is light or any signal, and the limit is absolute. This limit ties space and time together so tightly that they cannot be separated without breaking the rules of cause and effect. Another important point Feynman would stress is that space-time is not something added on top of the universe. It is not like a background grid drawn behind reality. It is part of reality. When physicists talk about the universe expanding, they are not talking about galaxies moving through empty space like dots on a balloon. They are talking about space-time itself stretching. The distances between galaxies grow because the fabric between them grows. Time is part of that story too, because the expansion unfolds in time and affects how we measure cosmic history. Thinking this way helps avoid many misunderstandings. For example, asking, what is the universe expanding into, assumes that space exists independently and that the universe is an object inside it. But if space-time is the universe, there is no outside space to expand into. The expansion is a change in the geometry of space-time itself. Feynman would remind you again that language often traps us. Words like fabric and stretching are metaphors. Space-time is not literally a cloth, and it does not ripple like water in a bathtub. These images are tools to help our intuition, not the reality itself. The reality is described by relationships between events, distances measured by light, and times measured by clocks. When those relationships change, we say space-time is curved or stretched. At this point, the idea that space and time are unified begins to feel less shocking and more inevitable. If the speed of light is fixed, if motion is relative, if cause and effect must be preserved, then space and time cannot remain independent. They must cooperate. They must become aspects of a single structure that adjusts itself to maintain the deeper rules of nature. Feynman would likely highlight how radical and yet how conservative this idea is. Radical, because it overturns centuries of intuition. Conservative, because it preserves what truly matters: the consistency of physical law. The universe does not play tricks. It follows rules, and when we discover those rules, even the strangest results fit together cleanly. He would also emphasize humility. The fact that space and time are one fabric does not mean we fully understand everything about them. At very small scales and very high energies, our current theories begin to struggle. Quantum mechanics and space, time do not yet fit together perfectly. This tells us that our understanding, while deep, is incomplete. But that does not weaken the idea. It strengthens it by showing that space, time, is a profound feature of reality, not a convenient mathematical invention. From an everyday point of view, you do not need to think about space, time to cross the street or cook dinner. But from a scientific point of view, ignoring it would be like trying to understand music without rhythm. Space, time is the rhythm of the universe. It sets the tempo at which things happen and the structure in which they unfold. Feynman would probably smile at this stage and say something like, "The universe is under no obligation to be simple, but it often turns out to be simple in a deep way." The idea that space and time are one fabric is not complicated because it uses fancy mathematics. It is complicated because it forces us to unlearn habits of thought that feel natural but are wrong. When you finally accept that space and time are inseparable, many questions change shape. You stop asking where things are in space alone, or when things happen in time alone. You start thinking in terms of events and relationships. You start to see motion, gravity, and even the history of the universe as expressions of space, time's structure. And this is very much in the spirit of Feynman's approach. Understanding does not mean memorizing formulas. It means seeing how ideas connect. Space and time being one fabric is not an isolated fact. It is a doorway. Once you walk through it, you find that the universe is not a collection of disconnected pieces, but a coherent whole, woven together so thoroughly that separating its threads no longer makes sense. When we talk about motion and perspective changing how space and time are experienced, we are stepping into one of the most surprising and unsettling ideas in modern physics. It challenges the quiet assumption that there is a single, correct way the universe looks and unfolds, regardless of who is observing it. In everyday life, perspective feels like a psychological thing. Two people may disagree about how beautiful a painting is or how loud a sound seems, but they agree on basic facts like how long a minute lasts or how long a table is. Physics once shared this assumption. Time was thought to tick at the same rate for everyone, and space was thought to have fixed lengths that did not depend on who measured them. Richard Feynman would explain that this assumption feels reasonable only because we live in a very narrow range of conditions. We move slowly compared to the speed of light, and we experience weak gravitational fields. Under these gentle circumstances, differences in perspective are so small that they go unnoticed. Nature politely hides its deeper rules from us. But when we begin to measure carefully, or imagine situations beyond everyday experience, we discover that perspective is not just a matter of opinion. It is built into the structure of space, time itself. To understand this, Feynman would begin with a simple idea: motion is relative. There is no experiment you can perform inside a smoothly moving spaceship that tells you whether you are moving or standing still. If the spaceship moves at a constant speed, the laws of physics inside it are exactly the same as if it were at rest. This was known long before Einstein, but it carried deeper consequences than anyone realized. If motion is relative, then measurements of space and time must also be relative, because they depend on how you move. Imagine two observers passing each other in space. Each believes they are at rest and the other is moving. This is not stubbornness or confusion. It is a fact of nature. Now suppose both observers measure how long a process takes, like a clock ticking or a particle decaying. Classical thinking says they must agree on the time because time is universal. But experiments show they do not. Each observer measures time passing normally for themselves, but sees the other's clock ticking more slowly. Feynman would emphasize that this is not because the clock is malfunctioning. Nothing is wrong with the clock. Time itself is behaving differently along different paths through space-time. Perspective is not about illusion. It is about how space-time assigns intervals of time and distance depending on motion. To make this idea concrete, he might ask you to imagine a beam of light bouncing between two mirrors, forming a simple clock. For an observer at rest relative to the clock, the light moves straight up and down. For an observer who sees the clock moving sideways, the light follows a longer, diagonal path. Since the speed of light must be the same for both observers, the light must take longer to complete its journey in the moving clock. That means the moving clock ticks more slowly. This conclusion is unavoidable. It comes directly from insisting that the laws of physics, including the speed of light, are the same for everyone. Here is where perspective reshapes reality. Each observer is correct in their own frame of motion. There is no privileged viewpoint. There is no universal referee clock ticking behind the scenes. Space and time adjust themselves so that the deeper laws remain consistent. What one observer calls a longer time interval, another observer may attribute to a longer distance. Space and time trade roles in subtle ways depending on perspective. Feynman would stress that this does not mean everything is relative in a loose or philosophical sense. The structure of space-time imposes strict rules. Observers may disagree about measurements, but they agree about physical events and causal relationships. They agree about what happens, even if they disagree about how long it takes or how far apart things are. Perspective also affects simultaneity, an idea that feels so basic we rarely question it. In everyday life, if two events happen at the same time for you, you assume they happen at the same time for everyone. Physics shows this is not true. Two events that are simultaneous for one observer may not be simultaneous for another who is moving differently. This is not a limitation of clocks or communication. It is a fundamental feature of space-time. Feynman would explain this carefully because it is one of the hardest ideas to accept. Imagine two lightning strikes hitting the ends of a train platform at the same time, according to an observer standing on the platform. Now imagine an observer riding on a train moving past the platform. Because the observer on the train is moving toward one lightning strike and away from the other, the light from the two strikes reaches them at different times. When they correct for the travel time of the light, they still conclude that the strikes did not happen simultaneously. Both observers are correct. There is no contradiction. Simultaneity depends on perspective. This realization forces us to abandon the idea of a single universal now. Each observer carries their own present moment, shaped by their motion through space-time. This is not a poetic statement. It is a precise physical result. Space-time does not come pre-sliced into universal moments. Different observers slice it differently. Feynman would likely pause here to point out how deeply this reshapes our understanding of reality. The past, present, and future are not absolute layers shared by everyone. They are relational concepts tied to motion and perspective. This does not mean that reality is subjective or that events can be changed by opinion. It means that time is woven into the geometry of space. Time and geometry depends on how you move through it. Perspective also plays a role when gravity enters the picture, even before we discuss space-time curvature explicitly. An observer standing on the surface of a planet experiences time differently from an observer far away in space. The one deeper in the gravitational field experiences time more slowly. Again, this is not a malfunction of clocks. It is a difference in how space-time is structured in different regions. Perspective, now defined not only by motion but by position in a gravitational field, changes the experience of time. Feynman would insist that these ideas are not abstract fantasies. They are tested every day. Atomic clocks flown on airplanes tick at different rates than clocks left on the ground. Satellites must correct for both their speed and their altitude to function properly. If engineers ignored perspective, modern technology would fail. What makes this especially powerful is that perspective does not merely affect our descriptions of space and time, it affects the quantities themselves. Lengths contract along the direction of motion. Time dilates. These are not optical illusions. If you bring objects back together and compare them directly, the differences remain. Space and time have been altered by the journey through space-time. Feynman would be careful to emphasize that no one ever experiences their own space shrinking or their own time slowing. From your own perspective, everything feels normal. Your heart beats at the same rhythm. Your ruler measures the same length. Relativity does not make reality feel strange from the inside. It only becomes strange when you compare different perspectives. This is one of the most profound lessons physics teaches. The universe does not privilege comfort or intuition. It privileges consistency. The laws of physics must hold for everyone, regardless of motion or location. To satisfy this requirement, space and time must become flexible. Perspective becomes a physical ingredient, not a mere viewpoint. At this stage, the idea that motion and perspective change how space and time are experienced no longer feels like a curiosity. It feels necessary. If the universe allowed one observer's measurements to be more real than another's, the laws of physics would break. Energy conservation, causality, and the speed of light would lose their meaning. Space-time solves this problem by making measurements depend on perspective in a precise and lawful way. Feynman would probably end this part by reminding you that perspective in physics is not about personal belief or interpretation. It is about how the universe measures itself. Different observers are like different measuring instruments, each revealing a valid aspect of the same underlying structure. Space-time is the language that allows all those perspectives to coexist without contradiction. Once you absorb this idea, the universe begins to feel less like a static stage and more like a dynamic network of relationships. Motion is not something that happens in space over time. Motion is a way of moving through space-time. Perspective is not something added by the observer. It is something the universe itself responds to, and space and time, once thought to be rigid and absolute, reveal themselves as flexible, relational, and deeply interconnected. To carry this further, it becomes important to see that perspective in physics is not just about observers watching from different places, but about the fundamental way reality organizes itself. Feynman would often insist that the universe does not care who you are or what you believe, it only cares about how you move and where you are. Perspective is built into the equations because motion and position are real physical facts. Once you accept that, it becomes clear that space and time cannot behave as rigid, universal quantities. Think about how we usually imagine motion. We picture an object moving through space while time marches on independently in the background. But in space-time, motion is a tilt. Different observers slice space-time into space and time in different ways. What one observer calls a pure passage of time, another sees as a mixture of space and time. This is not poetry, it is geometry. The geometry of space-time allows different observers to draw different grids over the same underlying reality. Feynman would emphasize that nothing mystical is happening here. The same events exist for everyone. The same causes lead to the same effects. What changes is how observers assign coordinates to those events. This is similar to how two people can use different map projections to describe the same Earth. One may distort distances near the poles, another near the equator, but both maps refer to the same planet. Space-time is the planet, space and time coordinates are the maps. This helps explain why arguments about who is really moving miss the point. There is no absolute motion. Motion only exists relative to something else. Space-time encodes this fact so deeply that it affects the measurement of time itself. The universe does not carry a master clock ticking away in the background. Each observer's clock is just as legitimate as any other. Feynman would likely draw attention to the idea that time dilation and length contraction are two sides of the same coin. They are not separate effects. They arise from the same geometric structure. When one observer sees another's time running slowly, that same observer also sees distances along the direction of motion shrink. These changes balance each other so that the speed of light remains the same. Perspective reshapes space and time together, not independently. This reshaping has a powerful implication. Reality is not built from absolute measures, but from relationships. The universe does not care how long a meter is or how long a second lasts in isolation. It cares about how events relate to each other through space-time. Intervals between events, not individual measurements, are what matter most. These intervals remain consistent even when space and time separately change from one perspective to another. Feynman would probably stress that this is where intuition often rebels. We want one perspective to be right and the others to be appearances. But physics refuses to grant that comfort. All inertial perspectives are equally valid. There is no hidden layer of reality where space and time return to their classical, absolute forms. The relativistic structure is the reality. Once this sinks in, many paradoxes dissolve. Consider the famous scenario where each observer sees the other's clock running slow. This feels impossible only if you secretly believe in a universal time. When you abandon that belief, the situation becomes perfectly consistent. Each observer is measuring time along a different path through space-time. Different paths have different lengths. There is no contradiction in different lengths being measured. Feynman would also connect this idea to the notion of proper time, even if he avoided the technical term. Each object carries its own clock, ticking along its own path. That ticking is personal and local. It does not need to match anyone else's ticking. When objects separate and reunite, they can compare clocks and discover real differences. Those differences are records of their different journeys through space, time. Perspective also teaches a deep lesson about humility in science. Our everyday experience gives us only a tiny sample of how the universe behaves. We live at low speeds and moderate gravitational fields, so space and time feel absolute. But physics shows that this is only an approximation. Perspective reveals layers of reality that are invisible to common sense. The universe is not strange to confuse us. It is strange because it is larger and more subtle than the conditions we evolved to handle. Feynman would likely highlight how perspective protects the consistency of physical law. If time were absolute but space were relative, or vice versa, the universe would fall apart logically. Signals could arrive before they were sent. Causes could follow effects. The unity of space-time shaped by perspective prevents these disasters. It enforces a structure where cause and effect remain intact for all observers. This brings us back to simultaneity, one of the most emotionally unsettling consequences of perspective. The idea that there is no universal no feels almost threatening. Yet physics does not remove the present, it multiplies it. Each observer has a present defined by their motion. These presents overlap in complex ways, but never contradict each other in terms of causality. Events that can influence each other always have a well-defined order. Events that cannot influence each other may have different orders for different observers. But that difference has no physical consequence. Feynman would likely say that nature is smarter than our language. We talk about past, present, and future as if they were universal categories, but space-time does not label events that way. It labels them by their relationships. What we call the present is simply the set of events that are nearby in space. Time to us right now. Change your motion, and that set changes. Perspective also reveals that observation itself is not passive. Measuring space and time is an interaction. To measure a distance, you use light. To measure time, you use clocks that rely on physical processes. These processes are governed by the same laws that shape space-time. There is no way to step outside the universe and measure it from nowhere. Every measurement is made from somewhere, moving in some way, embedded in space-time. Feynman would appreciate the elegance of this. The universe does not allow privileged viewpoints. Every observer plays by the same rules. This democratic structure is not a philosophical choice. It is forced by experiment. Whenever physicists tried to preserve absolute space or absolute time, they ran into contradictions. Relativity resolved those contradictions by embracing perspective as fundamental. From this angle, perspective becomes a creative force. It is not a limitation but a feature. Different perspectives reveal different aspects of the same underlying structure. Together, they give a fuller picture of reality than any single viewpoint could provide. Space-time is rich enough to accommodate them all. As you reflect on this, motion begins to feel less like something happening to objects and more like a way objects participate in the universe. To move is to choose a path through space-time. That path determines how much time you experience, how distances appear, and how you relate to other events. Perspective is not an add-on, it is the signature of your path. Feynman would probably conclude this line of thought by reminding you that understanding perspective does not require abandoning realism. The universe is real, events happen, causes produce effects. What changes is our picture of how those events are organized. Space and time are not rigid boxes. They are flexible dimensions shaped by motion, energy, and position. Once this idea settles in, many other concepts become easier to approach. Gravity, acceleration, black holes, and cosmology all rely on the same principle. Perspective matters because space-time matters. Motion and viewpoint are not superficial details. They are woven into the fabric of reality itself. And in the spirit of explaining it like you're 5, the lesson is surprisingly simple. The universe does not look the same from everywhere, and it does not tick the same for everyone. That is not a flaw. That is how it stays fair. By letting space and time change with perspective, the universe makes sure its deepest rules never break. The idea that light sets the ultimate speed limit of the universe is one of the simplest statements in physics, and at the same time one of the most revolutionary. At first glance, it sounds almost arbitrary, like a rule someone decided to impose. But Richard Feynman would explain that this limit is not a restriction added on top of nature. It is a deep property of how reality is built. Light does not merely move very fast, its speed is woven into the structure of space-time itself. Once you understand this, many strange consequences of relativity stop feeling strange and begin to feel inevitable. In everyday life, speed feels relative in a simple way. If you walk inside a moving train, your speed depends on whether you measure it relative to the train or relative to the ground. If you throw a ball forward while running, the ball's speed adds to your own. For centuries, scientists assumed light worked the same way. If you move toward a beam of light, you should measure it moving faster. If you moved away, it should seem slower. This assumption fits common sense perfectly. And yet, experiments showed it was wrong. Feynman would stress that this was not discovered by philosophical reasoning, but by stubborn facts. No matter how fast the observer moved, light was always measured at the same speed. This was not approximately true. It was exactly true within experimental limits. Nature refused to let light behave like an ordinary object. This forced physicists to confront a painful choice: either abandon the idea that the laws of physics are the same for everyone, or abandon the idea that space and time are absolute. Nature made the choice for us. The speed of light is not just very large, it is special. It is the same for all observers, regardless of their motion. This single fact reshapes everything. To preserve this constant speed, space and time must adjust. Distances can shrink, time can stretch, and simultaneity can break down, but the speed of light remains untouched. Feynman would emphasize that light is not special because it is made of photons, but because it reveals the geometry of space-time. Even if light did not exist, there would still be a maximum speed built into the universe. Light just happens to travel at that speed. One way to understand this is to think of the speed of light as a conversion factor between space and time. It tells us how much space corresponds to a certain amount of time. In equations, it appears everywhere, linking meters to seconds. This is a hint that space and time are not independent units, but different aspects of the same thing. Feynman would likely say that if we chose our units cleverly, we could even measure time in meters or space in seconds. The speed of light would then disappear from the equations, revealing even more clearly that space and time are unified. The idea of a speed limit immediately raises a question: speed relative to what? In everyday life, speed is always measured relative to something else. But the speed of light is not relative in that way. It is not the speed of light relative to the source or the observer. It is the speed of light relative to space, time itself. This is a strange statement, but it captures the essence of relativity. Space, time defines what speeds are possible, and light always travels at the maximum allowed speed. Feynman would explain that nothing with mass can reach this speed. The closer an object gets to the speed of light, the more energy it requires to go faster. As it approaches the limit, the required energy grows without bound. This is not because engines are inefficient or materials are weak. It is because space, time itself resists. The structure of reality does not allow massive objects to cross this boundary. This resistance is not experienced as a force pushing back. Instead, it shows up as changes in time and space. As an object moves faster, time slows down for it relative to slower observers. Lengths contract in the direction of motion. These effects are not side consequences, they are the mechanism by which the speed limit is enforced. Space and time rearrange themselves so that no matter how hard you push, you never exceed the speed of light. Feynman would also emphasize that the speed limit protects causality. Cause and effect depend on signals traveling from one event to another. If signals could travel infinitely fast, or if there were no maximum speed, the order of events could become ambiguous or even reversed. Effects could occur before causes. By imposing a universal speed limit, space-time preserves a consistent structure of cause and effect for all observers. This limit divides space-time into regions. For any event, there are events that can influence it and events that cannot. This division is not based on distance alone or time alone, but on a combination of both. Light defines the boundary. Events connected by light or slower signals can be causally related. Events outside that boundary are forever disconnected. This is not a matter of technology or patience. It is a fundamental limit of reality. Feynman would likely use a simple image to convey this. Imagine ripples spreading on a pond. The ripples move at a certain speed. If a leaf is too far away, the ripples will never reach it in time to affect its motion before something else happens. In the universe, light plays the role of the ripple. Space-time uses light to define what can interact with what. Another subtle point Feynman would highlight is that the speed of light is the same in all directions and for all observers. This symmetry is not accidental. It reflects a deep uniformity in space-time. There is no preferred direction and no preferred state of motion. The universe looks the same to all inertial observers, and the speed of light is the mathematical expression of that fairness. This fairness comes at a price: the loss of absolute time and absolute space. But Feynman would argue that this is not a loss at all. It is a gain. By giving up absolutes that were never directly observed, physics gains a framework that is internally consistent and experimentally accurate. He would also stress that the speed of light limit is not something you experience directly in daily life, because you are so far below it. Just as you do not notice the curvature of the earth when walking around your neighborhood, you do not notice relativistic effects when driving a car. But that does not mean the effects are not there. They are simply too small to matter under ordinary conditions. At high energies and large distances, however, the speed limit becomes unavoidable. Particles and accelerators reveal it clearly. No matter how much energy scientists pour into them, massive particles never reach the speed of light. They get closer and closer, but the limit remains untouched. This is not a failure of engineering. It is a triumph of theory confirmed by experiment. Feynman would likely point out that the speed of light also sets a limit on how fast information can travel. You cannot send a message faster than light. This means the universe has a built-in delay. Everything takes time to influence everything else. This delay is not a flaw. It is what allows the universe to have structure and history. Without it, everything would collapse into a single instant. He would probably smile at the idea that something as gentle as light governs the ultimate speed of reality. Light feels delicate compared to massive objects and powerful forces, yet it defines the boundary that nothing can cross. This is a recurring theme in physics. The simplest phenomena often reveal the deepest truths. Understanding that light sets the ultimate speed limit also changes how we think about motion itself. Speed is no longer just distance divided by time. It becomes a measure of how an object moves through space-time. When you move faster through space, you move more slowly through time. The speed of light marks the extreme case, where all motion is through space and none is left for time. That is why light does not experience time in the way massive objects do. Feynman would not overemphasize this last point, but he would appreciate its elegance. It shows again how space and time are intertwined. The speed limit is not an arbitrary wall. It is a geometric feature of space-time. Light traces the edges of what is possible. By the end of this explanation, the speed of light no longer feels like a curious fact about electromagnetic waves. It feels like a rule written into the fabric of the universe. Everything obeys it not because it is forced to, but because space, time itself, is built that way. Light does not race through space at the maximum speed. It reveals what the maximum speed is. This is why Feynman would insist that understanding the speed of light is not about memorizing a number. It is about seeing how deeply connected that number is to the structure of reality. Once you see that, many of the strange features of relativity stop being strange. They become the natural consequences of a universe with a built-in speed limit, a universe where space and time cooperate to make that limit absolute. To deepen this idea, it helps to recognize that the speed limit set by light is not experienced as a barrier in the ordinary sense. There is no wall you crash into, no sudden jolt when you approach it. Instead, the universe quietly reshapes the very measures you use to define speed. As you push an object harder and harder, adding energy to make it go faster, that energy does not translate into an ever-increasing velocity in the way common sense expects. It flows into changing the object's relationship with time and space. Time stretches, distances along the direction of motion compress, and the speed of light remains untouched. The limit is enforced not by resistance, but by geometry. Feynman would likely insist that this is the key to avoiding confusion. People often imagine that relativity adds strange effects on top of an otherwise classical world. In reality, the so-called effects are the world. They are how space-time maintains consistency. If time did not slow down for fast-moving objects, if lengths did not contract, then the speed of light could not remain the same for all observers. The universe would contradict itself. Relativity is not optional, it is the price of coherence. This perspective clarifies why the speed of light is the same for everyone, not merely for observers moving at constant speed relative to one another. Even accelerated observers who feel forces measure light's speed locally as the same constant. The rule is local and universal. Wherever you are, however you move, if you measure the speed of light right next to you, you will find the same value. This universality hints at something deeper than motion alone. It tells us that the limit is embedded in the local structure of space-time. From this angle, the speed of light becomes a ruler for causality. It draws a cone of influence around every event, separating what can be affected from what cannot. This separation is not negotiable. You can build faster machines, stronger engines, and more sensitive detectors, but you cannot send a signal beyond that boundary. The boundary is not technological, it is ontological. It defines what it means for events to be related at all. Feynman would emphasize that this structure is what prevents paradoxes from becoming real problems. If information could travel faster than light, then different observers could disagree about the order of cause and effect in ways that matter physically. A message could be received before it was sent. By enforcing a universal speed limit, space-time preserves a consistent ordering of causally connected events for everyone. Disagreements about time and distance are allowed. Disagreements about causality are not. It is also important to understand that the speed limit does not privilege light as a substance. Light is not fast because it is made of something special in a mystical sense. It is fast because it has no mass. Massless entities, whatever their nature, move at the maximum speed permitted by space-time. In this sense, light is a messenger that reveals the rules rather than a rule itself. If there were other massless signals, they would share the same speed. Feynman would likely point out how this reframes our understanding of energy and mass. As objects move faster, their energy increases dramatically, not because they are becoming heavier in a simple mechanical sense, but because their motion through space-time is changing. Energy and mass are two ways of accounting for how objects move and interact within this structure. The famous equivalence between mass and energy is another expression of the same underlying geometry that sets the speed limit. This geometry also explains why the speed of light connects so naturally to time. If you think of motion through space, time as having a fixed amount of motion available, then increasing motion through space leaves less motion available through time. At the extreme limit, all motion is through space and none remains for time. This is why light does not experience time in the way massive objects do. Along the path of a light beam, the interval of time experienced is effectively zero. This is not a mystical statement about consciousness, it is a statement about geometry. Feynman would caution against overinterpreting this idea, but he would appreciate its clarity. It shows that the speed limit is not arbitrary. It emerges naturally when you treat space and time as a unified entity. Light does not slow down time as a side effect. Time behaves the way it does because the structure of space-time requires it. Another subtle consequence of the speed limit is that the universe is inherently local. You cannot influence distant regions instantly. Everything propagates step by step, carried by signals that respect the limit. This locality is essential for the stability of physical law. Without it, the behavior of matter here could depend instantaneously on conditions arbitrarily far away, and prediction would become impossible. Feynman would likely connect this to the idea of fields. Forces are not actions at a distance in the old sense. They are mediated by fields that evolve in space, time, and transmit influences at finite speeds. Electromagnetic changes propagate at the speed of light. Gravitational changes also propagate at the speed of light. This universality reinforces the idea that the speed limit is a feature of space, time itself, not of any particular interaction. He would also emphasize how the speed limit shapes our picture of the universe on the largest scales. When we look at distant galaxies, we are looking into the past because light takes time to reach us. The universe has a horizon, not because it ends, but because there is a finite speed at which information travels and a finite age during which it has been traveling. The observable universe is defined by how far light has had time to go. This horizon is not a wall. It is a boundary of knowledge imposed by the speed limit. Beyond it, there may be more universe, but it cannot have influenced us yet. Again, the speed of light is not just a property of radiation, it is the rule that shapes what can be known and when. Feynman would probably enjoy pointing out that the speed limit makes the universe dynamic and historical. Because influences take time to propagate, the universe has a story. Events unfold, causes lead to effects, and structures form gradually. If everything were instant, there would be no meaningful sequence, no development, no evolution. Time would collapse into a single moment. The speed limit gives the universe room to breathe. At the same time, the limit invites humility. There are questions we cannot answer immediately because information has not reached us. There are events whose consequences will not be felt for millions or billions of years. The universe does not arrange itself around our curiosity. It unfolds according to its own rules, and the speed of light is one of the most fundamental of those rules. Feynman would also stress that this limit is not something that can be bypassed by clever tricks. Shortcuts, wormholes, and speculative ideas are interesting to explore mathematically, but they are constrained by the same underlying structure. Any consistent extension of physics must respect causality and the local speed limit, or explain precisely how those principles are preserved in a deeper way. Nature does not allow loopholes casually. From a pedagogical point of view, explaining the speed limit like you're 5 means emphasizing its fairness. Everyone gets the same rule. No observer is favored. No matter how you move, light behaves the same way. This fairness is what forces space and time to be flexible. The universe bends over backward to keep the rules the same for everyone. When you step back and look at the whole picture, the speed of light stops being a mysterious constant you memorize in school. It becomes the spine of space-time. It holds together motion, causality, energy, and geometry. It explains why time dilates, why lengths contract, why simultaneity is relative, and why nothing outruns light. Feynman would likely end this discussion with a reminder that understanding does not mean familiarity. You may never feel intuitively comfortable with a universal speed limit, just as you may never feel comfortable with the vastness of space. But comfort is not the goal, clarity is, and clarity comes from seeing how a single simple rule can organize an enormous range of phenomena without contradiction. In that sense, the speed of light is not just the fastest thing in the universe. It is the rule that tells the universe how to behave. Everything else follows from it, quietly and relentlessly, shaping the flow of time, the stretch of space, and the order of cause and effect. The idea that gravity is the bending of space, time rather than a mysterious pulling force represents one of the deepest shifts in human understanding of nature. For centuries, gravity was imagined as an invisible hand reaching across space, pulling objects toward one another. An apple falls because the Earth somehow tugs on it. The moon stays in orbit because the Earth's pull keeps it from flying away. This picture works well enough for everyday calculations, but Richard Feynman would point out that it explains very little about what gravity really is. It replaces one mystery with another. How does the Earth reach out across empty space to pull the apple? When gravity is understood as the bending of space-time, that mystery dissolves into geometry. Instead of asking what force pulls objects, we ask how space-time itself is shaped. Space and time are not rigid and flat. They can curve, stretch, and warp. Massive objects like planets, stars, and galaxies change the geometry around them. Objects moving nearby simply follow the natural paths in this curved geometry. What we experience as gravity is the result of following those paths. To make this idea intuitive, it helps to abandon the image of space as emptiness. Space-time is not nothing, it has structure. It can be distorted. Imagine again a smooth surface, like a stretched sheet. If you place a heavy ball in the center, the surface dips. Now roll a smaller ball across the sheet. It curves toward the heavier one, not because it is being pulled by an invisible force, but because the surface beneath it is curved. The ball is simply following the easiest path available. In physics, that easiest path is called a natural or straight path in curved space-time. Feynman would emphasize that this picture is only an analogy. Space-time is not literally a sheet, and gravity does not act downward into some higher dimension. But the analogy captures the essential idea: geometry replaces force. Objects move the way they do because of the shape of space-time, not because something is yanking on them. This perspective immediately explains something that puzzled scientists for a long time. In a gravitational field, all objects fall at the same rate, regardless of their mass, as long as air resistance is negligible. A feather and a hammer fall together on the moon. If gravity were a force like magnetism, this would be strange. Forces usually depend on the properties of the object being pulled. But if gravity is geometry, the mystery disappears. All objects follow the same space-time paths regardless of their mass. They are not being pulled, they are moving naturally through curved space-time. This also explains why astronauts in orbit feel weightless. They are not beyond gravity's reach. Earth's gravity is still strong where they are. But they are in free fall, following a natural path through curved space-time. They feel weightless for the same reason a falling elevator would feel weightless. There is no force pushing up against them. Gravity is not something they feel directly. What they feel as weight is actually the resistance of the ground or a chair preventing them from following their natural path. Feynman would likely stress this point because it overturns intuition. We think gravity is something we feel pulling us down. In reality, what we feel is the ground pushing us up. When you stand on Earth, space, time wants to guide you along a curved path inward, toward Earth's center. The ground stops you from following that path. That resistance produces the sensation of weight. Gravity itself is silent and effortless. Understanding gravity as curved space, time also explains why light is affected by gravity. In the old force-based picture, this was confusing. Light has no mass, so why should gravity pull on it? In the geometric picture, there is no confusion at all. Light always follows the straightest possible paths in space-time. If space-time is curved, those straightest paths are curved, too. Light bends near massive objects because space-time itself is bent there. This bending of light has been observed many times. Starlight passing near the sun is deflected. Distant galaxies appear distorted by massive clusters lying between them and us. These effects are not tricks of perception. They are direct evidence that space-time is curved. Light is tracing the geometry of the universe, making the invisible visible. Feynman would also point out that gravity affects time as well as space. In regions where space-time is more strongly curved, time flows more slowly. Clocks closer to massive objects tick more slowly than clocks farther away. This is not because gravity damages clocks. It is because time itself is part of space-time and is affected by its curvature. Again, this has been confirmed by experiment. Clocks on satellites tick at different rates than clocks on Earth, and these differences must be corrected for technology to work. Seeing gravity this way changes how we think about the universe as a whole. Planets orbit stars not because they are constantly pulled inward, but because they are moving through curved space-time in the most natural way possible. Stars orbit galaxies. Galaxies move through clusters. At every scale, motion follows geometry. This view also removes the need for gravity to be instantaneous. Changes in mass or energy do not instantly affect the entire universe. They propagate as changes in space-time curvature, moving at the speed of light. Gravitational waves are ripples in space-time itself, traveling outward from violent events like colliding black holes. When these waves pass through Earth, they slightly stretch and squeeze space. Their detection confirms that gravity is not a force acting across space, but a dynamic geometry that can ripple and evolve. Feynman would appreciate the elegance of this picture. One simple idea replaces many complicated ones. Instead of inventing a force with mysterious properties, we accept that space-time is flexible. Matter tells space-time how to curve, and space-time tells matter how to move. This single sentence captures the essence of gravity. At the same time, he would emphasize that understanding does not mean trivializing. The mathematics of curved space-time is complex. Predicting the exact motion of objects in strong gravitational fields requires sophisticated calculations. But conceptual simplicity matters. It tells us we are on the right track. From the perspective of explaining this to a child, the message is gentle. Things fall not because they are pulled, but because the world they move through is shaped. Heavy things change that shape more. Everything else responds by moving along the shape that is already there. Gravity is not an invisible hand grabbing objects, it is the quiet bending of the universe itself. Once this idea is absorbed, gravity stops feeling like a mysterious exception among forces. It becomes a natural consequence of living in a universe where space and time are not flat and rigid, but alive with structure. The idea that time does not pass the same way everywhere, for everyone, is one of the most emotionally challenging insights in physics because it directly confronts how we experience life itself. Time feels personal, steady, and universal. A second feels like a second whether you are happy or sad, young or old. We grow up believing that time is the same river carrying all of us forward together. Richard Feynman would approach this idea carefully, not by dismissing intuition, but by showing why nature refuses to follow it. At the heart of this insight is the understanding that time is not an independent background process ticking away identically across the universe. Time is part of space-time. It is shaped by motion and by gravity. How fast time passes depends on how you move and where you are. This is not a metaphor or a matter of perception. It is a measurable, physical fact. One way time changes is through motion. If you move very fast relative to someone else, your time passes more slowly compared to theirs. This effect is not something you feel directly. Your own heart, thoughts, and clocks behave normally from your perspective. The difference only becomes apparent when you compare clocks that have followed different paths through space, time. Experiments with fast-moving particles show this clearly. Particles that should decay quickly survive much longer when they move close to the speed of light. Their internal clocks run slow relative to the laboratory. Feynman would emphasize that this slowing of time is not caused by mechanical stress or damage. The particles are not struggling. Time itself is different along their path. Space, time assigns different durations to different journeys. Motion reshapes time. Gravity also affects time. The stronger the gravitational field, the more slowly time passes. A clock closer to a massive object ticks more slowly than a clock farther away. This is true even if neither clock is moving relative to the other. Again, this is not because gravity interferes with the clock's mechanism. It is because gravity changes the structure of space, time, and time is part of that structure. This means that time is not uniform across space. There is no single cosmic rhythm that everything follows. Instead, each location in the universe has its own pace of time, determined by the surrounding mass and energy. Each observer experiences their own proper time, the time measured along their own path through space-time. Feynman would likely point out how counterintuitive this feels. We want to ask which clock is really right. But that question has no answer. Both clocks are right for their own situations. Time is local. It belongs to the observer and the path they take. There is no master clock to appeal to. This has profound consequences. It means that aging is not absolute. Two people can start together and end up with different ages depending on how they travel and where they spend their time. This is not science fiction. It has been tested with atomic clocks on airplanes and satellites. The differences are small in everyday circumstances, but they are real. The idea that time flows differently also reshapes how we think about the present. There is no universal now, shared by everyone in the universe. What is happening right now for you may not be happening right now for someone moving differently or located elsewhere. Space, time does not divide itself into global moments. Each observer carries their own present. Feynman would stress that this does not destroy the order of cause and effect. Events that can influence each other always have a well-defined sequence. Time differences become ambiguous only for events that are too far apart to affect one another. This preserves consistency while allowing flexibility. Understanding that time does not pass the same way everywhere also deepens our sense of humility. Our experience of time is only one version among many possible versions allowed by space-time. The universe is not built around human clocks or human lifetimes. It operates according to deeper rules that remain the same even as time itself stretches and bends. This insight also explains why time feels so stubbornly one-directional in everyday life. Although space-time allows time to pass at different rates, it does not allow easy reversal. The direction of time is linked to entropy and the overall evolution of the universe, not to individual experiences of time slowing or speeding up. Feynman would remind us that relativity changes the rate of time, not its arrow. From a simple explanatory point of view, the lesson is this: time is not something you step into equally everywhere. It is something you carry with you. How it flows depends on how you move and where you are. The universe does not give everyone the same clock, but it gives everyone a fair one for their own journey. Once this idea settles in, time becomes less of a mysterious universal river and more of a personal path through space-time. That path may wind, slow, or speed up, but it is always real and always consistent with the structure of the universe. The idea that everyday examples can explain deep cosmic ideas was central to Richard Feynman's way of thinking and teaching. He believed that if you truly understand something, you can explain it in simple terms without hiding behind complicated language. This did not mean oversimplifying or distorting the truth. It meant finding the right picture, the right analogy, the right story that captures the core of an idea without losing its meaning. For Feynman, complexity was not a sign of depth, clarity was. He often pointed out that the universe does not change its behavior just because we are thinking about it. The same rules that govern galaxies also govern atoms and everyday objects. The difference is scale, not principle. This is why familiar experiences can be powerful tools for understanding the cosmos. When you connect an abstract idea to something you have seen, touched, or felt, it stops being alien and starts to feel real. Feynman loved to start with things people already knew. He might talk about throwing a ball, watching waves on water, or listening to music. These were not distractions, they were bridges. A ball thrown into the air follows a curved path. That simple observation opens the door to understanding motion, forces, and eventually gravity. Ripples spreading on a pond help explain waves, energy transfer, and even light. Music reveals patterns, frequencies, and resonance, which are fundamental to understanding vibrations and quantum behavior. The power of everyday examples lies in their honesty. They do not pretend to show the whole picture. They show just enough. A good analogy highlights structure without claiming identity. Feynman was careful about this. He knew that analogies can mislead if taken too literally. He used them as stepping stones, not as final answers. Once the intuition was built, he was ready to move beyond the analogy. One reason everyday examples work so well is that the human brain evolved to understand the world at human scales. We are good at understanding motion we can see, forces we can feel, and patterns we can recognize. Abstract mathematics and invisible dimensions are not natural to us. Examples translate unfamiliar ideas into a language our minds already speak. They reduce fear and resistance, making curiosity possible. Feynman would often warn against the idea that understanding means being able to recite definitions. You can memorize the words, space-time curvature, without understanding anything about gravity. But if you can imagine how a curved surface guides motion, you have the beginning of understanding. Everyday examples turn words into pictures, and pictures into insight. This approach also reflects a deeper philosophical stance. It suggests that the universe is not fundamentally opaque. Its rules may be subtle, but they are not designed to be inaccessible. With patience and creativity, even the most abstract ideas can be approached from familiar ground. Everyday experience becomes a laboratory for the mind. Feynman's use of simple examples also challenged intellectual arrogance. He disliked the idea that science should sound impressive or exclusive. If an explanation could not be made simple, he suspected it was not yet well understood. This attitude was not about lowering standards. It was about raising them. True understanding demands simplicity on the far side of complexity. Everyday examples also serve another important function. They reveal the limits of intuition. When an example works, it builds confidence. When it fails, it teaches caution. For instance, imagining space-time as a stretched rubber sheet helps explain gravity, but it also hides the role of time and can suggest a misleading downward direction. Recognizing these limitations is part of learning. Feynman encouraged students to enjoy the analogy, then let it go. This method of explanation mirrors how science itself progresses. Scientists start with familiar concepts, extend them cautiously, test them, and refine them. Everyday examples are not childish, they are foundational. They reflect the same process of building understanding step by step. In the end, explaining cosmic ideas through everyday examples is an act of respect for the listener. It assumes they are capable of understanding, given the right tools. It invites participation rather than intimidation. For Feynman, teaching was not about transferring information. It was about lighting a spark of curiosity that makes someone want to explore further. From this perspective, the deepest ideas in physics are not remote or mystical. They are extensions of the same patterns we encounter in daily life. The universe speaks a language that begins at home. Everyday examples are the first words in that language, guiding us gently toward the vast and the profound. The idea that curiosity and simple questions unlock complex truths sits at the heart of Richard Feynman's approach to understanding the universe. He believed that progress in science does not begin with grand theories or complicated equations, but with honest questions asked without fear of sounding foolish. Many of the deepest discoveries in physics began when someone dared to ask a question that others ignored because it seemed too basic. Feynman often reminded people that nature does not care about our pride. The universe responds only to questions asked clearly and tested carefully. Curiosity, in this sense, is not passive interest. It is an active desire to know how things actually work, even when the answers are uncomfortable or strange. Simple questions are powerful because they cut through assumptions. They expose hidden beliefs that everyone takes for granted. When someone asks, "Why does light behave that way?" or "What do we really mean by time?" they are not asking for decoration or philosophy. They are probing the foundations of understanding. Feynman would stress that simple questions are not simplistic. Asking "why?" at the right moment can be more difficult than solving a complicated equation. It requires intellectual courage. Many people learn to accept explanations too early. They memorize words and move on, never stopping to examine whether those words truly explain anything. Curiosity resists that temptation. It insists on clarity. This attitude explains why Feynman was so effective at uncovering errors and gaps in reasoning. He did not assume that widely accepted ideas were correct simply because they were popular or old. He tested them against simple reasoning and direct evidence. When something did not make sense, he kept asking until it either became clear or revealed a deeper mystery. Simple questions also have a leveling effect. They remind us that no one has a privileged position in understanding. A child can ask a question that reshapes an entire field. An outsider can notice a flaw that experts overlook. Science advances not because of authority, but because of curiosity disciplined by evidence. Feynman believed that the universe is understandable, but not in a way that flatters human intuition. Simple questions help bridge that gap. They allow us to approach complex structures without being overwhelmed. Instead of trying to grasp everything at once, we focus on one clear issue at a time. This step-by-step approach mirrors how understanding actually grows. Curiosity also protects against false certainty. The moment we stop asking questions, we start mistaking familiarity for understanding. Things feel obvious not because they are understood, but because we have grown used to not questioning them. Feynman warned that this is dangerous, both in science and in life. The habit of questioning keeps understanding alive. Another key aspect of curiosity is playfulness. Feynman often explored ideas simply to see where they led, without worrying about immediate usefulness. This playful exploration is not frivolous. It allows the mind to wander, make connections, and notice patterns that rigid thinking would miss. Many breakthroughs emerge from this relaxed but attentive state of inquiry. Simple questions also help distinguish between knowing the name of something and understanding it. Calling gravity a force or space, time curvature does not explain anything by itself. The explanation begins when you ask how that description connects to observation and experience. Curiosity refuses to settle for labels. Feynman would also emphasize that curiosity must be paired with honesty. Asking questions is not enough if one ignores answers that are inconvenient or unsettling. True curiosity follows the evidence wherever it leads. It accepts that the universe may not conform to our preferences. This honesty is what transforms curiosity into knowledge. From a broader perspective, curiosity and simple questions are not just tools for science. They are ways of engaging with reality. They keep us open, flexible, and humble. They remind us that understanding is always provisional and always deepening. In the context of explaining space, time like year 5, this lesson becomes especially clear. Complex truths do not require complex questions. They require sincere ones. Asking, "What is space made of?" or "Why can't anything go faster than light?" opens doors that technical jargon often closes. Feynman's legacy shows that curiosity is not a childish trait to be outgrown. It is a disciplined habit to be cultivated. Simple questions are not the opposite of intelligence, they are its foundation. Through them, the universe gradually reveals its structure, not all at once, but piece by piece. In the end, the power of curiosity lies in its refusal to be satisfied with appearances. It keeps asking until the picture becomes clearer. It accepts mystery without surrendering to it. And through this persistent questioning, even the most complex truths become approachable, understandable, and deeply human.